It's like, why the fuck are you in this class? Why are you here? At least you guys have lots of reasons to be here. Some of you are here because you have to be part of your curriculum and stuff, and that's fine. Yeah, it's just tough. Hey, Max. Yes, you did. You helped me find phyllo pastry. I really appreciate that. You saved my Thanksgiving. Yeah. So yeah, the acetal stuff, we realized it was on the MCAT, so we shoved it, crammed it into this course this year. Because we used to kind of say, well, it's in either one of these courses, that's fine. But then we realized there was a lot of students who weren't taking the second organic chemistry who were writing MCATs. And we want to make sure everybody here is in good shape for that if they're doing that. Okay. I'm going to share my screen because I'm not sharing my screen, so it's not really all that useful. So I don't know what came over me when I came up with the schedule, because I put 3 things on today, which were all really, really hard. I think part of my thinking on that is I did spend quite a lot of time. I think there's maybe 2 or 3 lectures in videos, like 3 hours worth of video covering the stuff that I have. I'm going to do a few examples of today if nobody else has any questions. So I guess I did quite a few examples in the lecture. So I thought, yeah, okay, I can do it a little bit less rigorously on this flipped class model. But yeah, there's a lot of stuff that's scheduled for today. So I guess I'm opening this first if any specific questions or anything anyone wants to ask. I'm buying myself some time by opening Pepsi. Because I'm really short on caffeine today. Oh, it's all on the schedule. It's just, I think it might have been 1 or 2. It just might have been extended ones. No. So all assignments always end the week before, as it says in the syllabus. So Friday, last Friday, is the last stuff you need to cover. Stuff now is for assignment 4. Yeah. Yeah, there's a lot of stuff here. Yeah, exactly. There's 4 parts to lecture 16. It's because there's so much detail here. There's a lot of stuff to practice with the mechanisms. So I do quite a lot of detail in that. So hopefully you get to see me do that kind of stuff. Mohammed, I can definitely cover that question while everyone else thinks of other questions that they've got. And so the question was basically excess of lithium aluminum hydride. So I think the reason this question is confusing is because we didn't see a lot of stuff with nitrogen in any of the examples I did everything with oxygen. If I rephrase this question, like this, by analogy, swap out nitrogen for oxygen. Melissa, your mic is unmuted and, you know, getting some background. Yeah, there we go. If you didn't be unmuted, that's fine, but I don't think you did. So, Mohammed, do you have a sense of maybe how to start this one? Okay, triple bond confuses you. Well, triple bond is just a double bond, but more so. The sounds of Essex Hall. Yeah. I'm in there right now. You can, luckily the construction's died down, but this morning was pretty awful. I actually had to move to do something yesterday and go sit in one of my labs with a lot of equipment because it wasn't running, which was good. So you would treat this the same as you would a carbonyl. First step. It's just without hydrogen. Now you have an oxygen. Now you have an aldehyde with excess lithium aluminum hydride. I think I can leave that in your hands. But let's see what would happen up here. It's exactly the same thing. Just because it's nitrogen, don't freak out. We're going to have the same pattern of reactivity. So we'll have a hydride attack the carbon that moves the electrons onto the nitrogen. Why does it attack the carbon and not the nitrogen? Because if we attack the nitrogen, we'll have a minus charge on the carbon. If we attack the carbon, we'll have a minus charge on the nitrogen. I know which of those I prefer. It's the nitrogen. It's further right on the periodic table. So we get that. Now, this is where it does get a little weird because of the double bond. I'm going to bind that to lithium because we got some lithium around from the lithium aluminum hydride. It's just I don't want N2 minus. Is that a covalent bond? God, no, but it will take care of some of that extra charge. It's just the lithium aluminum hydride is really, really reactive. Just for those who need it drawn out a bit more, I'll do an example of that. So we've added 2 hydrogens to that, and then on workup, we just get rid of the charges, right? And so that's going to bring it all the way down to just NH2. So a carbon nitrogen double bond, carbon sulfur double bond, carbon nitrogen triple bond, carbon oxygen double bond, carbon oxygen triple bond, carbon sulfur triple bond, carbon phosphorus double bond. See a trend here, double bonds between carbon and heteroatoms with lithium aluminum hydride. You get rid of the double bond and you stick in, like, you stick hydrogens everywhere. So the hydrogens on the carbon come from the lithium aluminum hydride. The hydrogens on the heteroatom come from the water. You always do workups at the end. Whenever you have charged things, so what did the questions say? So this one actually said, if I scroll back up to Mohammed's question, you can find it in the chat. It says, assume the reaction is carried out in tetrahydrofuran with aqueous acid added once the initial reaction is complete. So aqueous acid is water and acid. So notice in the practice assignments that I did, some of the products were left with the charge, no workup was done. So I think in the carbonyl one, I think in some places I explicitly said no workup. And so I left the charge on. In other cases, I think I always took it through to a neutral species. If the question doesn't say work up, then you can leave the charges. If the question explicitly, or you can either leave the charges or get rid of the charges. If it doesn't explicitly say it, you can assume it. And if the question explicitly says work it up, then you would put the charges on. I will, on the exam and on the assignment, anything graded, I will explicitly say either work up or do not work up. or I will indicate that by saying, you know, first one, use these reagents, second two, use water. So I will explicitly mention whether you're doing a workup or not. So in reality, you always resolve a reaction using a workup. You never don't do it. The only time you don't do it is if you're going to stick something else in, like you kind of have an intermediate. So there's one example in the assignment, the carbonyl assignment, where I had an alkyne, and I just said sodium hydride, no workup, and it was meant to kind of scaffold the question. So you deprotonated the right proton. Then the next question basically had that plus an electrophile, and so then you dealt with that and then did a workup. Okay, so Alyssa has a question. Okay, I think I actually asked a question very similar to this. Did we do this one already, or did I do this one in office hours? This is a stupid question. I will do it. I will do it under duress. It is a dumb fucking question because it doesn't actually work. So we did all of our acetal chemistry using acid. And the reason is because acid works. So it says sodium hydroxide, trace. Okay, so I think go ahead and close. First thing to realize whenever you're doing any reaction is what is the most reactive thing present, right? So Alyssa, give me that at least. Okay, is there anything charged? It's a hidden charge. The C double bond O is maybe OH minus, yes. Because remember, Na plus OH minus is charged. Yeah, okay, the C double bond O is an electrophile, that's true. But let's identify what the most reactive thing is in there, because it's great that you can identify a reactive electrophile. But let's make sure that we always, the risk there is that's great if I tell you, hey, Alyssa, I guarantee you this is a nucleophile electrophile problem. The thing is, sort of, you know, most stuff isn't that organized and this one's not. This is kind of tricky. So you need to always figure out what's most reactive. It's sodium hydroxide. Okay. So there's only a trace amount of it. Sodium hydroxide is both a base and a nucleophile depending on what it does, right? Like if it reacts with the hydrogen, it's a base. If it reacts with the carbon, it's a nucleophile. Remembering, now you can do this in a couple of ways, and we'll get the same answer in the end, but I prefer to shortcut it to get us the answer a little bit faster. The fastest type of reaction, I say this a lot in the lectures, and I think I've said it a lot in these flipped lectures too, are acid-base reactions. There is nothing faster than an acid-base reaction. When we start talking about SN1, SN2, which is next class, we are going to discuss why. But right now, just trust me. I never say just trust me, but I'm just saying just trust me because we're going to come back to this. Because you shouldn't trust me. Always be asking why. Sometimes the answer is I don't know. So we're going to deprotonate the most acidic proton on this molecule, which is definitely the OH. Okay. Now I have a nucleophile, and you're going to say, why did you're going to maybe ask, why did you do that? Instead of the other thing, it's like, because the other thing would end up here in the end. We like making rings. If you can make a ring, you make a ring. And by make a ring, I mean 5, 6, 7. But last class, we were seeing lots of 3-membered rings with those halogens, and that's fine too. With second row elements, they really like 5, 6, 7. The other ones are using d orbitals, and so their angles can be different. So that's why when we saw these iodoniums and things, we saw a lot of that. And the other thing is we had a big ass C+. And we wanted to stabilize that C+, we had something tied to it, so it was going to make the 3-membered ring. Here, we don't have anything massively reactive. Like carbonyls are reactive, absolutely, but a carbonyl is also stable. It's fine being a carbonyl. It has no great sense that it doesn't want to be a carbonyl. So when you can make a ring, you're going to make a ring. So this is why I'm using this oxygen instead of using the hydroxide, the OH minus from sodium hydroxide. Because if I did that, it would be in equilibrium and it would eventually end up with where we're going to go. Because rings are always more stable. So we do that. And then on assuming there's other hydrogens around, this will strip one off that and regenerate the alcohol. Why I don't like this is because, well, this one I'm actually okay with because it does form a ring. There was an example in a textbook where it did acetyl chemistry using base without a ring, and that just does not work. It's not stable. Rings are stable, so this is stable. This is actually very similar. This is the core functionality of ribose and deoxyribose, like famous for, you know, nucleic acid, DNA, RNA shit. And they make these rings. They're really an aldehyde and an alcohol. They're spaced apart by 4 carbons, and that cyclize onto each other, and they sit like this. So I don't know, did that, any other questions about that one, Alyssa, or did I get what you needed? Or does anyone else have any other questions about that? So we made the ring by, so if you're getting confused about this, sometimes it can be really helpful to number atoms. Numbering atoms never goes out of style. So let's do that. So 1, 2, 3, 4, 5, 6. And I'm drawing here that I have the oxygen, the O minus nucleophile, attacking the carbonyl, which is an electrophile. As Alyssa pointed out, it's a great electrophile. So we're making a new bond between atom 6 and atom 2. So there's 2, there's 6, and let's just finish counting. 3, 4, 5. So I've made a new bond between 2 and 6, and I've broken. So I'll take the H off the OH. Yeah, so it does throw you, like, so Alyssa, if what you were trying to do was saying, okay, like, look, I got this, NaOH attacks the carbonyl. This would be an okay way to start. So remember, everything is in equilibrium. So we have that. What we're stuck with here is we end up having, and if this gets worked up with water, like you know, we have some water somewhere, there's always water, I assume, then we deal with that charge. Okay. So what we've been doing is we've been drawing acetals where both oxygens are involved in ethers, and hemiacetals like this, where one of the oxygens, hemiacetal, is involved in an ether, and the other oxygen is an OH. Hemiacetals stable as rings. not otherwise. Acetals are stable. Hemiacetals are stable as 5- and 6-membered rings. This is a hydrate. What makes it a hydrate? There are no ethers. This is unstable. It's going to go back to being the carbonyl. So you can try and add it there, but the thing is it's going to go forward and going to go back. It's not going to do anything productive. The only way this is productive is if you can get to something stable, and a hydrate's not stable. So that OH directly attacking the carbonyl doesn't get you anywhere useful. Did that help? Great. Hydrates exist as intermediates. There are really specific cases where they can exist, and it's always surprising. Stable as rings, not otherwise, is what I wrote under their Fadila. As rings. Okay. So I think if I'm going to try and talk about two mechanisms, just do two problems, because I explained them in a lot of detail in the lectures. I don't think I'm going to do them any differently, but if you've watched the lectures, which I assume you haven't, because I would be absolutely swamped with questions coming in right now if you had. But I'm just going to give it as another option here. So what we've been doing a lot of is talking about, almost looks like an unhappy face. It's probably very appropriate for this course. I love this. I've dedicated my entire life to this. I completely understand that it is not for, I'm not going to say not for everyone. It's not for most people. And that's okay. And I don't hold it against you much. A little bit. I'm a little bit sad. But we've been talking a lot about Markovnikov addition of water. So we generate the more stable carbocation. Nucleophile comes into the carbocation. Everybody's happy. Hurrah. Okay, I'm glad. Do the problems. I think it was. I'm happy to come back and answer questions about that if you do them. Work through the problems in the assignment. Go back to so just all that stuff. Work through the problems in the assignment. Practice out the big mechanisms. I'm not a big fan of memorizing them. But I would actually say if we were doing in-person tests, you would need to memorize them. Instead, what I recommend you do is you memorize them on paper. So you practice them out, you understand how that works. And you can have it there next to you. You don't need to put it up here. You can have it in your paper next to you that you can then apply it to questions you'll get on an exam. But if you haven't practiced it a little bit, you're going to be completely lost for an exam. That is completely appropriate, Melissa. I think it was, if you actually did watch 4 hours of preparation for 1 hour like this, that would be, I admit, overwhelming. Okay, but let's talk about how we can do, what if I want that? I can't get that by adding acid and water. I can't. I can't. It's not possible because I'm going to generate the more stable carbocation. I'm never going to be able to put the more stable carbocation on a primary. So Alyssa, I think that is exactly the point. You need to understand the patterns of the mechanisms. Every molecule is different. You need to figure out what's going on there. And that's why I can have an exam, right? Because I feel for my colleagues over in, well, I don't really feel for them very much. Like over in fish biology, and they have an exam, and part of the exam was, here's a picture of a fish brain, label all parts of the fish brain. And they're very upset that students are at home and can have open book exams. It's like, well, how do I ask questions if they have an open book exam, because they can have the picture of the fish brain and they have all the labels for the fish brain? I would argue that anything that you can answer by looking it up in a book directly is not something I should be evaluating you on in an evaluation. It's kind of pointless because you can look it up in a book. So why should you be able to, why should you have to be able to regurgitate that? There is like a basic level of knowledge, but then what we want to do is we want to make sure that you can apply the knowledge. So that's what I'm doing, is I throw different molecules at you and I say, hey, think about how this changes that. If you understand the mechanism, because you've worked through it a bunch of times, I give lots of examples of it in the assignments. You practice it and you're like, okay, I think I understand why this is doing the thing it's doing. Then you get a new molecule, like, yeah, whatever. I understand how this molecule is kind of oriented, how this double bond is polarized, what it wants to do, and then I just work through it from there. So I guess my answer is you're not supposed to memorize stuff, because if you can memorize it, then you could just do it from a book. And if you can just do it by looking up in a book, why am I teaching you? Like, why are you here? Why don't I just say, fuck it, here's a textbook, the exam's in 12 weeks, see you then. Yeah, so I guess too much of the education system still relies on memorization. Anyways, my job is to help you try and figure out how to digest this stuff. I went on a rant this morning. I've been thinking a lot about this in the last 24 hours. Just particularly depressed. Okay, so I'm going to do borane, BH3. So how do we do this? Well, we don't make a carbocation. That's how we do this, because if we make a carbocation, we're fucked. We can't do this if we make a carbocation, so I need to not make a carbocation. I need to figure out a different way to introduce water. And the way I do this is called hydroboration deboration. So what this relies on is, let's think about this double bond. Let's think about, if you haven't seen this before, it's impossible to anticipate this. I'm going to ask a question. What way is a boron hydrogen bond polarized? If you need to, you can look up a periodic table with electronegativity values. H is minus. Perfect, Alyssa. Right, so all the time so far, whenever we've been attached to anything that's not carbon, H has been plus. But that's because we've always been to the right of carbon. Now, boron is to the left of carbon. Hydrogen and carbon are more or less equal. So like it's the neutral point, right? So this is polarized backwards. Okay. H is minus. Carbon is plus. Boron is plus. It's not a huge difference, but it's going to help us draw the mechanism. Okay, so if I think of it this way now, which way is my double bond polarized? You guys all got that right. It was awesome. Just double bond isolation. We've done lots of examples of this double bond. Yeah, C on the right is positive. Absolutely. Okay, So the way I have drawn that leads us to a challenge, right? I've got the positive next to the positive and a negative next to the negative. So that's not good. Okay. So let's redraw it. I like that more, right? We've got unlike charges near each other. Okay, that's why this is happening. The second reason this happens is on this. So this is the electronic argument. There's almost always a steric argument about size and an electronic argument about charge. And often they align, but not always. And sometimes one is really important, the other one's not important. And this is going to die on me in a second, so I'm going to plug it in. My writing is going to get worse because I'm going to start writing at a weird ass angle. I wonder if I can. No, I can't turn it upside down if it's plugged in because it thinks that I'm actually typing. Okay, so I'm just going to like hold it at an angle here. Which is bigger, the carbon on the right or the carbon on the left, size-wise? Takes up more space, which is more sterically demanding. These all mean the same thing. Perfect. Awesome. It, like, obviously, right? It's got two methyl groups. It's bigger. There's. Sorry, Madison. I think you meant right. I'm going to assume it was a brain fart. Like, this has got two big carbons on it. This has got two hydrogens. The one, yeah. Okay, perfect. There, we're good. So big. I'm going to write this in different ink. Small. Okay, similar for the boron hydrogen bond. Which one's big? Which one's small? Is the hydride, the H minus hydride, is that smaller than BH2 or is it bigger than BH2? Yeah, hydrogen is always smaller than anything. Like that's an easy one. Like the only thing hydrogen is bigger than is like an electron. And even then it depends. So just like with electronics, we want opposites. We always want opposite with sterics, right? We want the big thing with the small thing and the small thing with the big thing. Two big things don't want to interact together because they're both big and they both need lots of space. Like go back to your Newman projection discussion. We don't want big things near each other. So electronically, it wants to react like this. Sterically, it wants to react like this. Everything is pushing for the same way. Now, the mechanism is weird. And I'm going to draw it out because there's no way that this makes sense. Otherwise, the transition state for this has a four-membered ring intermediate, which I have probably explicitly said don't do when you're moving proton transfers around. I actually have said explicitly don't do when you're moving proton transfers around. Boron's weird. It's my defense. So what we have is like a delta plus, a delta minus. Should dot that line too. So all these lines are partially formed, partially broken. A delta minus, delta plus. Then this resolves to make that. So that's why we get this orientation. Now, I'm going to flip to the next slide. In the lecture, I know I walked through this next step, and it's just weird. This is, I think, the hardest mechanism in the course, which is why I'm covering it explicitly again, in case somebody else is kind of going, I don't get this, and then we can talk about it in real time. Okay, that's step one. So I said step one was add BH3. Step two was add sodium hydroxide and hydrogen peroxide. How do I know I'm done? It's neutral, and I don't see anything else that can really react. Okay. So again, the fastest reactions in the world are acid-base reactions. So I'm drawing this equilibrium. I'm saying it lies to the right. Anyone guess why? Notice I'm moving the charge from oxygen to oxygen, and I'm saying the charge lies to the right. There'll be a rationale for that. It's nothing you haven't seen before. It's just a little bit weirder version of it. It's not resonance. So we just focus on these two bonds. So if and let's just think about these. I'm just going to say R. There's something attached. There's no charge. Well, it's actually, Lauren, they are very unhappy. You're absolutely right. But what it actually has to do with is it's actually happier than the OH minus here, right? Because that's kind of buried the lead there. Sorry. I don't know if that helps anybody. An OH bond is polarized towards oxygen. An oxygen-oxygen bond is completely neutral by definition. So this oxygen is not receiving help from anybody for that negative charge. This oxygen can pull a little bit by induction. This oxygen here can stabilize part of this negative charge better than this hydrogen can stabilize part of that negative charge. So induction. Jesse, you're absolutely right that the charge. So Jesse said the charge is more spread out. That's her answer. And Jesse, you're absolutely right about that. And that is actually the answer to every single thing. Why is this charge more stable than that charge? The answer is always the charge is more spread out. But it doesn't actually answer the question. It's like, why is this surface wet? If I walk into my kitchen first thing in the morning and I'm stumbling around and I step in a pool of liquid and I say, why is this surface wet? The answer isn't because there's water on it. I want to know, why is there water on it? Did my dog pee on it? Did my cat play in the fountain overnight? Is the roof leaking? Is the toilet overflowing? It would be really bad if the kitchen is wet because the toilet's overflowing. There's lots of causes for why the tile is wet, but the water's wet. Yeah. The floor could be wet because of induction too. That is also possible. Anyways, so we generate this guy. It's really nucleophilic for a reason that nobody quite understands, called the alpha effect. Heteroatoms attached to other heteroatoms are just super nucleophilic. There's a lot of hand waving out there. You can look it up and there'll be explanations. I don't believe any of them. I just don't think they quite cover it. I have one I really like, but I have no evidence for it, and it is way too complicated for us to talk about. All this to be said, we've got a great nucleophile. And what we're going to do is we're going to play Boron Chemistry, which is a very fun game. So right now, the boron I've drawn up there in the top left-hand corner is neutral. It's got 6 electrons. Now the product of what I've drawn is negative. But it's got 8 electrons. So that's good, but it's negative. So it's neutral. Boron, and this is why boron's weird. Boron is neutral with 6. Nothing else is neutral with 6 that we talked about, right? You always have a charge. You end up with 6 electrons. Like for oxygen, it's the kiss of death. It doesn't happen. For carbon, we're getting pretty used to them. Boron, it's normal. It's fine with 6 electrons. It also really likes having 8 electrons. But if it's got 8 electrons, it's negative, and it doesn't want to be negative, so it wants to have 6 electrons again. So how does it do it? The arrow I'm about to draw is one which I still don't like. It's right. You know what? I'm going to draw an intermediate, and let's see if this makes any sense of anything. This is not an existing intermediate. I'm going to break the oxygen-oxygen bond. I don't know. Maybe this will help. If not, I don't draw it in a lecture, so you can. If this doesn't help, you can ignore it. Not that I'm saying that everything else is going to help either. This is just hard. So if I do that, I've just done what I said you should never do, which is made an oxygen with positive charge. Now, this does not exist. I am not drawing something real. But what we ended up here now is we have a negatively charged boron next to a positively charged carbon, but they can't make a bond because boron's already making 4 bonds. But I don't want a positively charged oxygen. But what if I break a bond to boron and make a bond to oxygen? So I'm going to kind of play the shuffle. And I'm going to break this carbon-boron single bond, which is pretty pathetic anyways, because boron-carbon bonds aren't super strong. And I'm going to make a new oxygen-carbon bond. And if I do that, I've never drawn it this way, so I don't know if this makes more or less sense than how I normally do it. You can compare, because you can see how I normally do it in the lecture. We make this new thing, and we've dealt with all the charges. The boron's no longer negative, the oxygen's no longer positive. And then it's just aqueous workup. Water with a bit of acid, cleave the boron-oxygen bond, because it's kind of like a metal. Boron, it's on the. As an organic chemist, everything to the left of carbon's a metal as far as I'm concerned. As far as astronomers are concerned, everything heavier than helium is a metal. They're crazy. The inorganic chemist would disagree with me and say boron is a metalloid and not a metal. And I'd say they're just too picky and need to get a life. So we get the alcohol out of this. And note, we went back to what the overall thing that we were trying to do here was we were trying to add, we had this carbon double bond. I'm just going to draw it with the same orientation as what I've ended up drawing there. And we wanted to do an anti-Markovnikov addition of water. And we've succeeded. So this is the hardest mechanism in the class. The second hardest mechanism in the class. No, maybe that's the second hardest mechanism in the class. The hardest mechanism in the class is ozonolysis. I think I have an entire lecture on ozonolysis. And I'm not going to try and do that in 4 minutes because I will do a shitty job. So I don't know. Anyone got any questions about hydroboration? When you get a test mark back, those should be being marked this week. You should get those back early next week. I'm sorry, it should have been marked last week, but we had a fire that we had to deal with, and so suddenly I spent the entire week in meetings about fires, and so I did not get that done. Surprise. Yeah, this was a hydroboration. Can you explain what happened after the second square bracket? So after these brackets. So what we did was we broke this carbon boron bond. There was a bond between carbon and boron, or 2 electrons there, and they just kind of shuffled over to the oxygen. It's almost like they just pivoted. They went from being bond to boron to being bond to oxygen. Boom. So why did they do that? Because just look at that thing I drew in square brackets. It's got a B minus, it's got no plus. It's just a fucking disaster. Look at the thing I've drawn after square brackets. No charges. That's why they did it. So they pivoted from here to here, just up. And suddenly all of our problems went away. So this is actually called a 1-2 shift, because something shifted from one atom to the second atom, which is attached to the first atom. So, 1, 2, and this thingy shifted from 1 to 2. Depending where you are, this course has an awful lot of 1-2 shifts in it of carbocations. I'm choosing not to do that because it's complicated and we don't need to. How do we take the boron off? Acid and water, basically. So how this works, I can talk about this in a bit of detail. Let's expand that. That's absolutely fair. I think I draw it in my answer keys to the questions. So if we have, boron attached to something. Sorry. Boron attached to something, then if I treat this with acid and water, I protonate the oxygen. Now I'm not going to make a B+. That's not what boron wants to do. So I can't break this bond. What I can do, though, is take advantage of this whole thing where boron doesn't know what it wants to be. Like basically where we all are in our lives. And boron's like, you know what, I'll try out being negative for a moment. Now suddenly it makes sense that we can break that bond. Because if we do that, oh look, we have an alcohol. And now boron's back to being neutral. And it's attached to maybe some positive water. But you can take a water molecule, take off one of these hydrogens. And we go to that. So Jesse and Madison, does that answer your questions? Oh, so Olivia, it's still there. I just stopped drawing it. It's still there. It's just it became implied because I don't need to draw on all the hydrogens and all the carbons. I probably should have kept it though because it was an important hydrogen because it was kind of like the whole purpose of this. Okay, good. And I know I've answered your specific question. I know I haven't answered all your questions because you're not quite sure what questions to ask because it's all really overwhelming. I get that. Faith said, so is hydroboration just anti-Markovnikov with BH3? Yes, that is exactly what it is. You can also do it with BH and different R groups. So BH3 works. Equivalently, one of the most common ones is something, you know what, I don't want to draw it. I'm just going to draw boron dicyclohexyl. So this also gets used. but it's basically the same thing. The boron dicyclohexyl is a little bit better because I said, hey, look at the size difference between BH3 and H. Yeah, H is a lot smaller than BH3. H is a whole lot smaller than this. So yeah, really good control over which carbon this attacks. Yeah, no, that's good, Olivia. So yes, hydroboration is anti-Markovnikov addition of boron. The deboration is swap the boron for oxygen. And for that step, so overall, if you do a hydroboration followed by the deboration, which is what we just did, you end up doing an anti-Markovnikov addition of water. And the reason it's anti-Markovnikov is we get the opposite product from what you would get from the Markovnikov. And the Markovnikov is the one you get from the most stable carbocation. So the only way to do anti-Markovnikov chemistry is to avoid making carbocations in the first place. Why wouldn't the BH2 stay attached to the oxygen because isn't that molecule stable? Alyssa, yes, it is. What we're going to do, though, is you only have a little bit of this guy in there. We're going to add a metric ton of water. And so we're just, because, you know, this is the same, right? Right, the two, sorry, those aren't the same because one's charged and one's not. So the two things here I'm highlighting in blue. As far as the boron's concerned, those are pretty similar, right? We can agree on that. Like, I agree with you. The molecule on the left is pretty stable. What we're going to take advantage of the fact is I've got a little bit of this. I add a freaking ton of water. And I'm just going to make use of Le Chatelier's principle. I've got tons of water on the left-hand side of the equation, and I'm just going to push down the concentration gradient. I'm just swamping it with water. So the only reason I make more of this is because I can use up the water and I liberate the other guy. So it's purely an argument based on adding lots and lots and lots of water. But you're absolutely right. That is a stable molecule on the top left-hand side. You can actually isolate that. You can do things with it. Similarly, the molecule with the boron attached, 50 years ago, we would have done what I just did, always. Now, we actually want to make things like that to do other types of chemistry with them all the time. We're not going to talk about that chemistry in this class. But making carbon-boron bonds are very stable as well. So there's multiple places where this is stable. And we're just constantly we're trying to, we actively have to go out of our way to destabilize it. Okay. I think it's my nap time. So I think we're good. I'm going to stop there for today. Yeah, have a really good rest of your Wednesday, and I will see you guys all on Friday. And hopefully we've got the marks back for you early next week. And again, apologize for the delay there. It's a really long delay. I get that.